In this video, we give an introduction to chance models that is used in our Introduction to Statistical Investigations curriculum. This example is typically done during the first week of the semester and shows how we introduce students to inference. A famous study from the 1960s, Dr. Bastian explored whether two dolphins, named Doris and Buzz, could communicate abstract ideas. During a training period, Dr. Bastian placed buttons underwater on each end of a large pool, 2 for Doris and 2 for Buzz. Then he used an automobile headlight as his signal. When he turned the headlight on and let it shine steadily, he intended for the signal to mean, push the button on the right. When he let the signal blink, that meant, push the button on the left. Every time the dolphins pushed the correct button, Dr. Bastian gave them a reward of some fish. Eventually, Doris and Buzz caught on and earned a fish reward every time. Then Dr. Bastian made things a bit harder. Now Buzz had to push the button before Doris. If he didn't push his buttons in the correct order, no fish. After a bit more training, the dolphins caught on and again could earn a fish reward every time. The dolphins were now ready to participate in the real study to examine whether dolphins could communicate with each other. Dr. Bastian took away Buzz's headlight and placed a large canvas curtain in the middle of the pool. Dr. Bastian then turned on the headlight and let it flash. He watched to see what Doris would do. After looking at the light, Doris swam near the curtain and began to whistle loudly. Shortly after that, Buzz whistled back and pressed the button on the left. He got it correct, and so both got a fish. But this single attempt was not enough to convince Dr. Bastian that Doris had communicated with Buzz through her whistling. Dr. Bastian repeated the process several times, sometimes having the light blink, and other times having it glow steadily. He kept track of how often Buzz pushed the correct button. In one phase of the study, Dr. Bastian had Buzz attempt to push the correct button a total of 16 times. In this sample of 16 attempts, Buzz pushed the correct button 15 out of 16 times. There are two possible explanations as to why Buzz pushed the correct button so many times. The first is, he's just guessing he got lucky in those 16 attempts. And the other is he's doing something other than just guessing. Perhaps there's real communication going on. It's certainly possible that Buzz was just guessing and got lucky, but does it seem like a reasonable explanation? Do you think Buzz knew which button to push? One approach to decide between these two possible explanations is to choose a model that represents Buzz randomly guessing and see whether this model is consistent with the observed data. Because Buzz is choosing between two options, the simplest chance model is to consider a coin flip. We can flip a coin to represent or simulate Buzz's choice of assuming he's just guessing which button to push to generate our artificial data. We can let heads represent the outcome that Buzz pushes the correct button, and tails be the outcome that Buzz pushes the incorrect button. The chance of heads, of course, is the probability that Buzz pushes the correct button if he's just guessing. And one set of 16 coin flips represents one set of 16 attempts by Buzz, or one simulated trial. Now that we see how flipping a coin can simulate Buzz guessing, let's flip some coins to simulate Buzz's performance. Remember that heads represents Buzz guessing correctly and tails represents Buzz guessing incorrectly. And we need to flip 16 coins to match Buzz's 16 attempts in the actual study. Here we got 6 heads and 10 tails. This gives us an idea of what could have happened in the study if Buzz had been randomly guessing at which button to push each time. Let's flip our coin another 16 times and see what happens. This time we got 10 heads and 6 tails. The dot plot shown here is keeping track of the number of heads. Buzz's actual result of 15 out of 16 is more extreme than either of these simulations of Buzz just guessing. Let's flip our 16 coins 98 more times for a total of 100 sets. Again, we see from our dot plot nothing as extreme as 15 heads out of 16 ever happened. Let's think carefully about what the dot plot is showing us. Each dot represents the number of heads in one set of 16 coins, or the number of times Buzz correctly guessed which button to push if there's no communication going on. We might consider any outcome between 5 and 11 heads to be typical, but getting fewer than 5 or more than 11 is a bit unusual. We refer to these results as being out in the tails of the distribution. Let's now flip our coins 900 more times for a total of 1,000 sets. Again, we see nothing as extreme as 15 heads out of 16 ever happened in our 1,000 repetitions. This shows us that 15 is a very unusual outcome, far out in the tail of the distribution of simulated statistics. In short, even though we expect some variability in our results for the different sets of 16 tosses, the pattern shown in this distribution indicates that an outcome of 15 heads is outside the typical chance variability we would expect to see when Buzz is simply guessing. Therefore, we have strong evidence that the by chance alone explanation is not a good one for Buzz, and something other than random chance was at play. And perhaps that other thing is that Buzz and Doris are communicating. Let's review what we have done to assess statistical significance by summarizing what we call the 3S strategy. We observed a sample statistic, the number of times Buzz pushed the correct button out of 16 attempts. Then we simulated could-have-been outcomes for that statistic under our chance model of just guessing. Finally, we evaluated the strength of evidence by observing that 15 out of 16 was way out in the tail of our simulated distribution. Since something as extreme as 15 out of 16 would rarely occur by chance, we say our observed result is statistically significant.